precession, or at least moves in a way that's not consistent with precession. I'm still working on that. There's a lot of work to do on that to understand it. We need many hundreds of years to look at it to make sure what's going on there. But so you can see Orion here is the best way to look at find Sirius, and you can see it coming up after Orion. Sirius will come up after Orion from the horizon. And the Egyptians, of course, were using it for regulating their year, and they would wait for that to occur, Sirius to rise up just before the sun. So typically, some of the data shows around July 20th, they would do what's called a heliacal rising. But if you look through the three stars of Orion's belt, it points directly at Sirius, and it's the easiest way to find it. It's the brightest star in the sky. And so that's always seems significant to me. The criticism of that is that any star that they use to regulate their own calendar, they would want to have a bright star, and also Sirius is located in the right part of the sky for their use. The Egyptians used this as a sidereal type alignment, star-based alignment. They needed something bright and a star that preceded the annual flood. Now that's the thing. Their cycle, their yearly cycle, was much more consistent than the Babylonian world, which flooded periodically, had all kinds of problems with them. The Nile Valley is much more stable. They had thousands of years of very stable kinds of things. For some reason, the waters came down at a pretty predictable time. And there's more to this calibration of their calendar. It's a complicated story where around Jubilees, this 1,461-day cycle comes up, because it takes about 4.5 years, or 4 years to completely have the star come back to the same location. And it's a complicated story, but it does show that they were really watching it very carefully. And it was used to regulate all their other civil calendars and all that. So here's Sirius. It's in the right part of the sky for the Egyptians' use. It has a little bit of motion. It's interesting. The Julian calendar came out in Julius Caesar's time, and that was based on we think now as a mistaken assumption that it was 365.25 days, or close enough, maybe, is what they thought. And it's actually slightly less than that. It's 0.243, something like that. Well, Sirius, it turns out, tracks the Julian calendar beautifully. It's almost exactly 365.25 because of the slight, what's called proper motion, going against precession. So it ends up being a very good marker for that. Obviously these people had looked at this star for many years, and they've been watching it, and they seem to see something special about it. And again, it does. I still go back to the notion. It is also a very bright star. It's in the right part of the sky for their use. The big question that I've been dealing with is, and I still don't have an answer to this, is why didn't Sirius precess? There's evidence that July 20th would be, even this year, would be close to being a heliacal rising if you were to go now. Maybe it's August. I've heard also August 5th. It's probably closer to that now. But with the Egyptian era, it should have been 3,000 years, 4,000 years ago. We should have seen Sirius move much more than it has, according to records. And the astronomers who are living today have done very careful, proper motion studies of Sirius. They say it's precessing fine. So it's a mystery. The other odd thing is that in ancient times, it was called a red star. And now we clearly can see it's a bright white star. It's blue to our eye oftentimes. So these are things that, it's going to take years to sort this out. It also has a companion. Sirius B is a red dwarf. And that perhaps could explain it, but it turns out the cosmologists, the astronomers say no, that it wouldn't be the right color for that star. It would still be a lot of a detritus around the star if it had blown up in that recent a time. It had to have, if it did any collapse or anything to make itself into a red star, it would have to have happened a long time ago from what they know of other stars. So also red shifting and blue shifting. Let's go over that real quickly. We talk about the yugas that in the binary theory that Walter's been working on. Before the year 500 AD, Sirius would have been going away from us, and now it's coming towards us. And actually, it is coming towards us at about 7,000 kilometers a second, and which is actually pretty small compared to some of the other motions of other stars. But it's, oh, not small, but it's less than, say, some of the other stars. So it's coming towards us. It should turn to the blue spectrum. So as it goes away from us, we all know that things turn red. They do what's called a redshift as they go away from us. And then they go, when they come towards us, it's a blue shift. Well, it turns out that that's not really a color, that's a direction. A slight motion towards you is called blue shifting, and a slight motion away from you is called red shifting. Doesn't mean that the color of the star would actually change. That's an important thing to know. I had to find out from an astronomer about this, that you read some of the astronomer blogs, and they make fun of this whole binary star theory, and one of the things that they do talk about each of these issues and come up with an explanation. So here's Karl. He passed in 2008. He was very well thought of in his little town of Piers, Alberta, in Canada, near Edmonton. I read the eulogy of him, and he seemed to be a very interesting character, and Walter knew him and has told some very interesting stories. Quite a character. He came out and just started a piece of land in near Edmonton all by himself and his family, of course, and carved out a pioneering lifestyle. And he, very creative. He was a master technician, very, very brilliant man. So he had a background in a lot of math and electronics also. It was not just lathe work that he had done also. His conclusion was that the lunisolar model is wrong. He's pretty convinced that from some of the readings he had done for the 60s and 70s that Sirius was not moving, wasn't precessing. And so that's what he went into in 1988, I think it was. Yeah, 2000, yeah, so it was about 1988, the very end of that year, he found out that Sirius A and Sirius B were going to be in alignment with the Earth, with our sun. And he was curious what was going to happen. And so he wanted to start reading, watching for it. And all you do with a meridian transit reading is you train a telescope due south. He was unable to do that, so he went to the southwest, which is perfectly acceptable as long as it doesn't change. You get aberration effects if you get too far to the horizon, but there was no concern of that. And he was just looking for that repeatability each day. He evidently, and Walter can confirm this, I think you could see Sirius even during the daylight if you knew, and you had a telescope and you knew right where to look and at certain times of the day. Then he would track it. He had the clock in Fort Collins, Colorado, atomic clock information right in his home, so that he knew to the very second. And some of his readings are within a half a second, or they're at about a half a second. He could determine the exact center of the reading that accurately. And Walter had actually the experience of doing that one day he was there. So his initial interest was in this, and sorry, let me go back just to make sure we understand. So Sirius A and Sirius B were in alignment. He knew in early '89, so he started reading and starting the setup in late '88, and took this data here that he talks about. Now, normally this data, this is a normal year, and this is what he found in the year right at the time when the Sirius A and B were aligning. You'll notice that it's negative and it goes into the positive regime afterwards. He claimed that it was negative during the time it's actually meaning slowing down the Earth's rate. No, sorry, I should probably explain the graph. It's a day length variation. In other words, how much does each day vary compared to the Fort Collins clock? And that is a very clever thing to do. I'm really quite impressed with that idea, because Fort Collins is dead accurate. It's based on a 365.243 day, whatever the actual number is. And they track precession. They know exactly what in order to get us 86,400 seconds a day reliably over time, with slight adjustments they make every now and then for what are called leap seconds. So when you're looking at here, this is a 235-second variation each day. That's expected variation. This is the unexpected variation. This is the variation from that actually calculated value of 235 seconds a day. And so, very clever way to do this. You want to look at the error. That's a very common thing in engineering too that you look for. You look for the errors are usually easier to measure.